Hey y'all, it's your main math teacher, Mr. Boyd, and I'm back at it again today because we're going to be introducing polynomials. For today's lesson, it's going to be helpful if you have access to Desmos, whether you do that on your computer or on a phone. You could also use a graphing calculator of any kind, that would work just fine, but we're going to be pretty visual today, and there are going to be things during the video that I'm actually going to ask you to pause the video and try on your own with graphing software, so that'll be important. Okay, the big idea of this video and the one that's going to follow it, which will be lesson 4, is we're going to try to sketch the graph of polynomials when we have the equation. So we'll get into what all that means in a second, but it's going to be really visual and we're going to be doing a lot of sketching. So let's talk about what a polynomial is. We've already seen polynomials that look like these, and we haven't really used that vocabulary yet, but actually these are both parent functions for polynomials. We called this first one f of x, we called that the quadratic, and then we called the next one the cubic. We're going to get into more exciting versions of those. So that'll mean a few things. It means the powers are going to get a lot bigger than 2 and 3, and also there's going to be multiple terms. Just like in our previous 2 lessons where we looked at quadratics where they had 3 terms, we're going to be looking at things with more terms. So let's get into the general form. In general, a polynomial function is one of the following form. Okay, let's break this down. Don't get symbol shock here. Okay, here's the key features. You have x being raised to some power, x being raised to a smaller power, x being raised to a power that's smaller still, okay, squared first. So we saw this the other day. We had an example like 3x squared plus 5x plus 2. Okay, now that matches this last section perfectly. So this little guy is just a number. 5 is like a sub 1. The x is just the x. So we've seen things that look similar to this. We've just never seen one this long. What this business in the middle about is saying, it's just saying we don't know what the biggest power is. It's some positive integer. So notice it is a positive integer. And I'd also like you to know that largest power is called the degree of the function. Okay, so no need to get too freaked out about this. Let's play a quick little game and see which of these down here is a polynomial so we can kind of compare our understanding of the definition to what we see. Let's start with A. Is this a polynomial? Yeah, absolutely. The exponents are positive integers, and there's nothing else weird that would prevent it from being so, so that's a yes. What about the next one? That's a no. This one right here, that translates as x to the 1/2 power, and it says right here, positive integers. 1/2 is not an integer. Okay, so this is a no. What about the next one? Now I'm trying to trick you a little bit on this one because I've got the exponents out of order, so it goes to the 4th to the 7th. We have 1 first power all the way down here, and I also put a decimal. Now it doesn't give any restrictions up here about what the a values are, and they could all be different, they could all be the same, makes no difference. But there's no restriction. They can be decimal, that's fine. So this is actually a yes. And with the last one, this chunk in the middle, yeah, that part's a polynomial, but the fact that there's absolute value bars, I mean, this is a big ol' no. All right, now for Desmos time. So go ahead and pull up your computer, pull out your phone, pull up your graphing calculator, whatever you're going to use, and I'd like you to graph each of the following: x squared, x to the 4th, and x to the 6th, and try to answer that question, what do they all have in common, and then make a prediction, what would y equals negative x to the 6th look like? And then when you're done with that, hit play, and I'm going to show you what I think. Okay, here's what I get on Desmos. I've got x squared, x to the 4th, and x to the 6th all graphed out right now. Okay, and so what I notice is those all are kind of cup-looking things. So the red one's the parabola. These other ones are not parabolas, but they both point up all the way. What about when you put a negative 6 in there? Or negative x to the 6th, excuse me. Making it negative just flips it, like we'd probably expect. So both ends are pointing in the same direction. Now, let's look at another prompt so we can have something to compare that with. I'd also like you to graph x cubed, x cubed, x to the 5th, and x to the 7th, and see what they all have in common and make a prediction about what negative x to the 7th would look like. So pause now. Okay, I'm going to turn these off. I'll turn these guys on. And so look, again, similarities. So they both have, or all three of them have this sort of S-curve feature to them. On the right, they're pointing up, and on the left, they're pointing down. Okay, so I'm going to go back and I'm going to record those key features for myself. What do they all have in common? So I'm going to put both sides pointing up. Or, in the case of this one, both point down. And that contrasts a little bit with the ones that were, notice these are the even numbers, that contrasts a little bit with the odd numbers. So on the ones that were odd, one side pointed up, the other down. So let's take a look then at a couple other cases. Let's look at this one right here. We already know what x to the fourth looks like. Let's compare that to x to the fourth with all this extra junk on the back, a minus 3x cubed plus x squared minus 5, and see if that changes this fact or not. Okay, so I'll get rid of these. We'll pull back x to the fourth, we'll pull up that one, and let's see if that changes it. So what we had recorded is that on x to the fourth, both sides pointed up. Even with all these modifications, it still points up. And I can go in here and I can change these and see if it still works. So I make that a plus, yeah, both sides are still pointing up. I could make this a minus 10 or a plus 10. Let's make it a minus. Yep, both sides still point up. Let's make this a plus 15, how about? And I got to zoom out so I can see what's going on. And sure enough, both sides still point up. So here's how we classify these. What we're going to do, we're going to look at the degree. The degree is the largest exponent. That's 4. That's going to tell us if we have this feature where both sides point up or both sides point down. Let's see if that holds up for this cubic as well. So we'll get rid of these, bring back the cubics. And yeah, look at that. So this one just has a little extra wobbly-do in the middle, but yeah, that still holds up. And you can go through and play with these if you want. So I'll mess with the coefficients a little bit and see if they still have those characteristics. Yeah, it seems to still hold up. So when it's modified, what features are unchanged? Well, the main feature we recorded, that one side points up and that the other points down. So with that said, let's talk about end behavior. End behavior simply means what's happening on either end of the function when it's not doing any more wobbling. Notice, so like this down here, it's pointing downward, and then in the middle, it does some wobbly stuff, but in the end, it ends up pointing down again. That's what we mean by end behavior, because the function doesn't end. It goes on forever, but it's just saying on one side after it's done doing all of this oscillation, what is it doing? So here's how we write that, and this is going to be really formal, okay? On this one, we would say as x approaches infinity, and that arrow means approaches, y approaches, so infinity, x approaching infinity, that's a positive, that goes to the right, so as we go to the right, x goes down, x approaches negative infinity. And then we'll do the other side as well. As x approaches negative infinity, meaning we're going to the left. Now, guys, notice that I get that arrow points to the right. That translates as approaches. It's not saying we're literally moving to the right. It's not a direction. It's just because we're reading left to right in the English language, okay? So x approaching negative infinity means x moving to the left. So as I trace it to the left, I end up going up. So that means as we go to the left, y ends up going up. So we say y approaches infinity. Why infinity? Because it goes up forever, right? That's the idea. So what about this one? As x approaches infinity, y approaches, it's going down on the right, so y approaches negative infinity. And as x approaches negative infinity, y approaches, so going negative infinity on the left, it goes down, so negative infinity. Why don't you try the last one? On this one, as x approaches infinity, y also, it goes up and to the right, so those are both positive, so y approaches infinity. And as x approaches negative infinity, y is going down on the left, so y approaches negative infinity. Hey, let's go back for a second and talk about the degree of each of these. And as it relates to what we've talked about so far, I'm wondering, just by looking at these, can you tell me anything about what the degree of each of these equations had to be to produce these graphs? Like, for example, this one in the middle, both ends are going in the same direction, which tells you what? It's very similar to when we graphed x squared, x to the fourth, and x to the sixth. So what I would know about this is that the degree was even. The largest exponent was an even number. What about this one? The end behavior is alternating, meaning one's positive, one's negative. that means it must have been an odd degree. Now, I don't know. It might have been 3 or 5 or 7. I really don't know, but I know that it was odd. What about this one? Alternating end behavior. So this one is odd as well. Okay, so this gets us to a bigger question. How can we know the end behavior of a polynomial just by glancing at the equation that made it? So let's see if we've already looked at any examples of any of these, like a positive coefficient with even degree. So let's scroll up for a second. Positive coefficient, so in this one, the coefficient's 1, and it's an even degree. What did that one look like? It looked like kind of a weird W thing, kind of like that. So here's what's important. Both of those were going up, and that's what this little task is asking us to say. Okay, so I'm going to make a little sketch in here as a visual to remind myself, because I'm a visual learner, maybe you are too. Looks something like that. And I'm going to show a different bit of notation. So what we did a minute ago right here, we said as x approaches positive infinity, this is what's also called right hand end behavior. And then x going to the left, that's what's called left hand end behavior. So I'm going to write it in that notation down here. So for even and positive, I have up, up. So I'm going to make a note. In that case, the left hand is positive and the right hand, hand is positive. Let's look for one that we had with a positive coefficient with an odd degree. So where do we have one of those? Looks like right here. Positive coefficient because it's 1, degree 3 because it's odd. And that did something like this. Up on the right, down on the left. So very similar to this one. So I'm going to make a note of that. It was something like this. So the right hand was going up, so we say right hand positive. Left hand was going down, so we say left hand negative. So when it was even, they were the same. We saw that in the very beginning. That was in number 1. So when it was a negative coefficient, like we had negative x to the 6th, it went down on both sides. And so that would tell us that the left hand is negative, left hand pointing down, and the right hand is also negative. What about an odd degree? We had negative x to the 7th we'd graphed. Oops, if I did it backward, whoops. And that looks something like this. So on that one, the left hand was positive and the right hand was negative. So this simple little chart captures pretty much every pattern we've looked at so far. You can tell by looking at the leading coefficient and the degree of the polynomial what the end behaviors will be. Positive and even, positive, positive. It's pointing up on both sides. Remember, even, they're going to match. So it's either positive, positive, or negative, negative. Odd, and I will add this in here so we have it for reference. Odd was alternating. Oops, I need a thinner pen. Alternating. Okay, and that's why it goes plus minus and minus plus, although I've switched right and left here. And the stuff that goes with them is right, but that's why it looks like plus minus, plus minus. Left is positive, left is negative on that one. So let's try these. I'm going to ask that you use your learning so far, use the chart that you have in your notes, and try it. Describe the end behavior of these, then graph them to check your answer. I am going to come in and fill in the answers here in just a second, so give it a pause and see what you can come up with on your own. One thing that I hope you've noticed is that most of the information here is not necessary to answer the question, because we're only looking at the leading coefficient, the one that has the greatest power. So really, all of this tells us nothing. Okay, we're going to look right here. That's positive, and we're going to look at the degree. So that's a leading coefficient. The degree is even, and so if it's even and positive, what that tells me is that my right hand end behavior is that it's going to be positive, and that my left hand end behavior, since it's even, they're going to match, is also going to be positive. Or if you want to write it the way we did the fancy way, you'd say as x approaches negative infinity, y approaches infinity, and as x approaches infinity, y still approaches infinity. Okay, what about number 2? What's the extraneous information? We're only looking at the largest power. And so we have a negative here, and we have an odd there. Okay, so remember, odd means that they alternate. The negative means that on the right it's going to go down, and on the left it's going to go up. Now, what I've drawn here, that is not a sketch of this graph. This is probably going to do all kinds of weird stuff. I don't know. But what I know It's odd, so it's alternating, and if it's negative, that means the right side will be down. So I can say that my left hand end behavior is positive, and my right hand is negative. What about this last one? Only the leading term matters. I have a positive and even, so my right hand is positive and my left hand is positive. They're both going to point up. So let's try these. This will be our last thing, and this is really a review, but I think it relates a little bit to what we've done today. We're going to try to sketch each of these without the use of a calculator or without graphing software. Pause the video and try it. Check yourself in Desmos or watch the rest of the video to see how you did. Okay, so here's what I'll remember. If it's x to the 6th, that means it's going to be up and up. So when I go to graph this, all I have to do is identify the transformations. That's on the inside, so that's shifting to the right, and that's shifting up. So 1, 2, 3, 4, 5, up 1. And it does something like that, and it's probably a little bit skinnier than that, but that's my guess. What about this one? This one again, x to the 6th, same parent function, but it's shifted down 1, no left and right, but this one is stretched by the 3, so this one I want to demonstrate that that's thinner. All right, y'all, that's our introduction to polynomials. Hope you enjoyed the video, and we'll see you next time.